the channel. I'm the GCSE science teacher, and in today's video we are going to be talking about reacting masses and mole calculations. This is for GCSE chemistry, so if you are currently studying GCSE chemistry, give this video a like, share it with someone else you think would also benefit from learning more, and let's get into it. Thank you so much, by the way, if you've already subscribed. It's amazing to have you here. I am a real life science teacher, and I do make videos on all the different topics for biology, chemistry and physics GCSE. I also make content on TikTok and Instagram as well. All of it is at the GCSE science teacher. So like I said, today's video we're going to be talking about mole calculations and continuing with quantitative chemistry. But we first need to start off by looking at balancing equations, because this is going to really underpin everything we do moving forward. Balanced equations, why we even balance equations in the first place, is to make sure that the number of atoms on each side are the same. So for example, if we look at the examples I have here, we have A plus B, which are the reactants on the left-hand side of the arrow, and they go to form AB, which is a new product on the right-hand side. In some cases, you will have a reversible reaction arrow, and this just tells you that the reactants can make products, and the products can break back down and make the reactants. So the reaction essentially goes two ways. For the sake of today's video, we are just talking about one-directional reactions, so like the first one above, the ones that you're pretty used to seeing all the time in chemistry. Something to be aware of as well is when you have to balance equations, you can only use coefficients to do this. The big number in front of the molecule or compound, you can't change the subscript number, the little number next to it. For example, CO2, carbon dioxide, you can't change the 2 next to the oxygen. You can only put numbers next to the carbon in front of it. And that's because you would otherwise change the chemistry of that compound or molecule, and that's something we can't really do. So we would only essentially balance equations by adding coefficients, and I'm going to give you some examples of how to do this now. Also, any of you who are cake lovers like myself, this is just a bit of a visual for you. If you have all the different ingredients for a cake, they combine together to make a new product. For example, flour, eggs, sugar, that kind of thing, all combine together chemically to form something new. We, in this case, can't reverse that reaction. This is a non-reversible reaction. We can't just break that cake down and get all the components again. But also notice that the cake is made up only of the components on the left-hand side. Nothing new has been added out of nowhere. So that's kind of this idea of conservation of mass. You can't create something out of nothing. That's why we balance equations, to make sure the number of atoms and the types of elements on either side are the same. So let's have a go with an example of balancing equations. So here we are. We've got a very common equation. So we've seen this before. This is a glucose molecule reacting with oxygen, and it's forming carbon dioxide and water. So you've probably seen this equation before when glucose is broken down with oxygen as anaerobic respiration. Remember, the reverse of this reaction is actually photosynthesis. So they are exactly opposites of each other. But we're going to balance this equation now. And some of you might be already thinking, oh, I already know what this is. It's just 3 numbers, I already know. But how do we get those 3 numbers? So let's start off by saying step number 1, we want to separate the reactants from the product. So wherever the arrow is, draw a straight line down the center, or an arrow straight down the center, so you have those separated. Next, what you want to do is write out the symbol of each of the elements on the reactant and product sides, and you'll notice that they're going to be the same. There's carbon on each side, hydrogen on each side, oxygen on each side in this example. There's never going to be one side that only has nitrogen on it, or one side that only has sulfur on it. They have to have the same elements on either side because of that law of conservation. We can't just create something out of nothing, okay? Next, what you want to do is you want to write out the number of atoms for each of those elements. So in this case, so far, we have 6 carbons on the left-hand side, but 1 carbon on the right-hand side. And I've done the same for each of the other elements as well. And you can see that there. Now, I have started to look at the other compounds and add them as a total. So for example, when it comes to oxygen, you can see that it's 8 because we've got 6 from the glucose and 2 from the oxygen diatomic molecule. Okay, so that's why it's a total of 8. So just be very careful when you are balancing equations that you are taking into consideration all the molecules, all the compounds, all the formulas on either of the sides. It's really important to do that. Something also to mention at this point is if you see brackets, you want to times everything inside the bracket by the small subscript number. That way you will get the correct answer. But there's no brackets in this case, so we're good to go. Next, what you want to do after you've written out the number of atoms of each element, you want to check if those elements have been balanced. So in the case of carbon, like I said, to begin with, we had 6 on the left side, 1 on the right hand side. They weren't balanced, and none of it was balanced actually. So you want to start to add coefficients to make them balanced. And as you can see, we've started to add multiples of things. So I've noticed at the beginning that carbon, there was 6 on the left and 1 on the right. So the only way to increase that carbon number on the right-hand side is to add a 6 in front of the carbon dioxide formula. And that essentially changed the number of carbons to 6. So carbons are now balanced, but it also changed the number of oxygens there. So 6 times 2 is 12. That ultimately changed the number of oxygens on either side, because we had to consider, okay, well, how many hydrogens are there? If we're adding a oxygen there, if we're adding hydrogens, that is something to also consider too. So one thing I will say with this sort of method of balancing equations, it's going to be kind of messy. You're going to always need to write out things, practice. I would recommend you start off by adding multiples of 2 to either side if you're not sure. That way you can check and see which ones have increased. What you're trying to do is trying to find a factor which will increase that number so all of the elements are balanced. This was a bit of a whistle-stop tour of balancing equations. I do and will move on to the next part of this lesson. But if you do want some more support and more detailed support about balancing equations, just let me know in the comments down below and I will make a video dedicated to it. That's absolutely fine by me. Okay, so mole calculations. We've already talked about moles. I'll link a card of the video I did previously on it. If you are not sure, I really recommend you go and check that one out. But for those of you who have watched that video and you're now onto this one, moles are a part of the course in quantitative chemistry where you need to actually calculate either the mass of something, the relative formula mass, which essentially takes into account the mass of the atom, and you also need to be able to calculate the number of moles in a question. And you do this by using this equation. So moles are equal to the mass of the substance divided by the relative formula mass, or the MR. Sometimes this can also be called the AR. The difference is that the MR is looking at the formula. Okay, so for example, carbon dioxide is made up of more than one atom, CO2, and that therefore means it has a formula. The AR, the atomic mass, if it's just, say, for example, iron, Fe, it's just one atom. So it's just the mass of that atom comparative to carbon 12. Okay, and you can find that information. Where do you find it? Well, you find it in the periodic table. You're looking for the mass number, the biggest number that is there. That's the number you're using when you are trying to deduce the MR or the AR. So these are some questions then. Calculate the mass of 0.30 moles of carbon dioxide molecules. And we've been given the MR, and the MR of carbon dioxide is 44. Where does that come from? Well, like I said, you go to the periodic table and you look up carbon, which is 12, the mass of it. You look up the oxygen, and you would find that it's 16. And there's 2 lots of oxygen in carbon dioxide. So we do 16 plus the 12 carbon, and that will give you an answer of 44. So that's where that number comes from. Like I said, if you do want maybe a short or a video that's a bit shorter on MRs, ARs, I am more than happy to do those as well. So what you do, first step, whenever you do a calculation in science, you want to write out the equation. And I have put it into a triangle for you. You can use this if you want to rearrange. If you are using triangles, just be aware to remember where those bits in the triangle go, but also remember as well the units for each of them. You can see in the question we have 0.30 mole. That's the unit for moles. Scientists have just, for some reason, they've just chopped the E off, and that somehow is more efficient, but here we are. So and you can see if we do 0.30 times 44, we get an answer of 13.2. And we want to make sure that we are writing the correct units because it's asking us to calculate the mass, so it's going to be in grams. And we can see the same for another question. It says calculate the mass of 0.15 moles of iron. Iron has a relative atomic mass of 56. So we're doing the exact same thing as before, and you can see my working out there. Okay, so let's have a look at how these questions can get more challenging. So we've gotten the first essential steps, but this is where you're looking into the more challenging, more complicated questions, because there's a lot more steps to it. So I'm going to run through a couple of examples with you, and feel free to pause the video at any point if you need to go back and remember what I said a minute ago. that's the beauty of videos, you can do that. So let's have a go. The question is, calculate the mass of nitrogen needed to make 300 grams of nitrogen monoxide. So they will give you in the exam a periodic table, so don't worry about that, but they will also give you an equation. So the reaction you can see is nitrogen, N2, and it's in a gaseous form because of the state symbol there. It reacts with oxygen, also a gas, and it forms 2 lots of nitrogen monoxide. Remember, monoxide is just one oxygen. Okay, that's why it's NO. All of them are gases. So we're needing to do a couple of things. The first thing I recommend you do is in step 1, and it's to identify what you know from the question and what you don't know and what you need to know. So we can see in the question it says calculate the mass of nitrogen. So I would recommend underneath the equation you have, or the formula, the reaction you have, you draw a little question mark like I have. That's what we're trying to work out, the mass of nitrogen. But we know there is 300 grams of nitrogen monoxide that are made. And I've also put that underneath the nitrogen monoxide. Oxygen, nothing is mentioned about oxygen, so we don't need to worry about it. We can just leave it as is and ignore it. The next step you want to do is work out the MR of each substance, because we can do that without any other information. And we know that we need to work out the MR because we know we need to work out the mass of nitrogen. And the only way we can do that is by having the MR and the number of moles. We don't have the number of moles currently, but we can work out the MR. Okay, so that's what we need to do next. So I've just gone into the periodic table and I've calculated the MR. If, like I said, if you want a more in detailed video on how to do that, I'm more than happy to do it. I just want to speed up. There's too many steps otherwise, so just let me know if that's something you want. I can also leave some comments in the description box below as well to help you with that if you're struggling. So once we've got the MR, we then want to calculate the number of moles of the known substance. So the known substance in this case is nitrogen monoxide. So the way we work out the moles is we rearrange our triangle equation and we have moles equals mass divided by MR. So the mass of nitrogen monoxide is in the question, so it's 300 grams divided by the 30, which is the MR. When we do that, we get an answer of 10 moles. Now what we do in step 4 is we want to look at the ratio, the relationship between the product that we have and the information that we have there versus what we're trying to actually work out. So the ratio between nitrogen and nitrogen monoxide in this equation is a 1-to-2 relationship. Now, how did I find that out? Well, nitrogen on the left-hand side, it has no big number in front of it, no coefficient. And that tells us as scientists that there is a big number 1 there. It's just invisible. We don't need to draw a 1 in front of it because there's one lot there that's already been drawn. If there was more than 1, we'd draw 2, 3, 4, etc. So it's 1. There is a big 2 in front of the nitrogen monoxide. So that tells us that the coefficient is 2. So that's where we get that ratio. So that just means if we have 1 lot of nitrogen, we make 2 lots of nitrogen monoxide. So if we had, for example, 10 moles of nitrogen monoxide, we actually have half as much nitrogen. So that gives us an answer of 5 moles of nitrogen because we've just divided it by 2. Okay. And we can do the opposite. We can say, well, if we've got 5 moles of nitrogen, we would then have 10 moles of nitrogen monoxide because we're just timesing it by 2 because it's a 1-to-2 relationship. So once we have that information, we now know we have 5 moles of nitrogen when we look at the ratio. Okay, we can then rearrange our equation to figure out the mass of nitrogen. So the mass is equal to the moles times the MR. We know the moles of nitrogen is now 5. We're timesing it by the MR of 28. And then we should see the answer of 140 grams. And that is our answer. Underline it, make sure the units are there, and we're good to go. Okay, so this is a go for you. Pause the video, have a go, comment down below what your answer is. I will also leave the answer in the description box below. So if you are wanting to know the answer, it will be there. But have a go for yourself. Make sure you use the steps to success to help you out. I'll be very excited to see what you have to say on this one. Thank you so much for your time. I have been the GCSE science teacher and you have been curious. If you did enjoy the video, please feel free to like it and subscribe, join our community, share this with someone you think would also benefit from learning more. And if you do have any video suggestions or you want support with anything in terms of biology, chemistry or physics GCSE, do let me know in the comments below. You can also find more of my content on my Instagram and TikTok at the GCSE science teacher, where I post regular supportive information, tips and tricks, and exam success techniques. So thank you so much, and I'll catch you in the next one. Take care. Bye.